In the first part of 2.4, we talked about finding the mean and the standard deviation for a data set. So now we're going to use those concepts to figure out when data entries are unusual and very unusual. So we're on our way to be able to determine how to identify outliers. So data entries are considered to be unusual if they are more than 2 standard deviations from the mean. So if our mean was, say, 10 and our standard deviation was 2, then if a data entry was, so the mean is 10, if I go 2 standard deviations above, so it would be 10, 12, 14, any data values that would be more than 14 would be considered unusual. Same way if I go the other way, if the mean is 10, go -2, -4, so any that would be below 6 would be considered unusual. Data entries are considered very unusual if they are more than 3 standard deviations from the mean, either above or below. So these are concepts, guidelines that we're going to use for the future as well. So keep in mind, data entries are unusual if they are more than 2 standard deviations from the mean, very unusual if they are more than 3 standard deviations from the mean. And remember, that can be above or below. So kind of there's sort of a double-edged sword there, because if you have unusual data values, then they have a stronger effect on mean and standard deviation than those values that are close to the mean, because remember that what we do is that we square the differences between each data value and the mean in order to get standard deviation. So if you have unusual data values, then your standard deviation is larger, which makes it more difficult to identify unusual data entries. So it's kind of bizarre. I'm going to write out what I just said about the effect on standard deviation. Unusual and very unusual data values have a greater effect on standard deviation than values that are close to the mean have, because we square the deviations. So we're going to talk about something that's called the empirical rule, and it has to do with bell-shaped distributions. So we're going to use this bell-shaped distribution graphic here in a moment. Now there's a general guideline for data that has this distribution shape. And that data follows what we call the empirical rule. It has another name that's weird and long and does help you remember the values, but it's called the 68, 95, 99.7 rule. So for a data set that has this bell-shaped distribution, remember we looked at that. It was a symmetrical distribution. We talked about it last time. And we said, or I said, that the mean would be near the middle of that distribution. And that's also where the median is and the mode. And what happens is within this distribution, if you are at the mean and you move 1 standard deviation above the mean, then 34% of the data will be in that zone. If you're at the mean and you move 1 standard deviation below the mean, then 34% of the data will be in that zone as well. So if you're within one standard deviation, that includes above and below the mean. So that's where that 68% comes from. 68% of our data values would be within one standard deviation of the mean. Now, if I go 2 standard deviations above and 2 standard deviations below, 95% of the data values would be within 2 standard deviations. So we have the 34 above and below with the first, and then 13.5% above and below with the next one. Going 3 standard deviations above and below would cover 99.7% of our data values. So there's 2.35% in each of them. So that leaves 0.3% would be 3 standard deviation, more than 3 standard deviations away from the mean. So 0.15% in the right end tail and 0.15% in the left end tail. So the guidelines for the empirical rule is that it applies to a data set that is approximately symmetric and bell-shaped. It doesn't have to be perfect. And just like this graphic shows, the 68 part of the name comes from knowing that 68%, about 68% of data values lie within one standard deviation of the mean. And then about 95% lie within 2 standard deviations of the mean. And the last one, of course, about 99.7% of the data values lie within 3 standard deviations of the mean. Now, up at the top of the page, when we first started, we were talking about unusual data values and very unusual data values. So we said that unusual data values are more than 2 standard deviations from the mean. So we've just said that 95% of our data lie within 2 standard deviations of the mean. So that means that 5% of data entries could be considered unusual. Very unusual lie within more than 3 standard deviations from the mean. So since 99.7% of our data is within 3 standard deviations of the mean, that leaves 0.3% of our data values that would be considered very unusual. Let's look at an example of using the empirical rule. So go ahead and get this example taped in. We're going to be using information from a survey conducted by the National Center for Health Statistics. They have given us the sample mean height of women in the United States, ages 20 to 29, was 64.2 inches with a sample standard deviation of 2.9 inches. We're going to estimate the percent of women whose heights are between 58.4 inches and 64.2 inches. So what we'll do is we'll draw ourselves a little symmetric distribution, because it doesn't specifically state it in here, but I can tell you that the height of humans does follow that symmetric bell-shaped curve. So we'll sketch a little sketchy sketch of that, and we're going to start labeling the mean and then some standard deviations. You may remember doing this in Algebra 2. So there's my not great sketch of the normal curve, but excuse me, not the normal curve. We're calling this the symmetric or bell-shaped curve. Later, we'll call it the normal curve when there are specific other requirements that it meets. So my apologies. So what we're going to do is we're going to label the mean. Remember that the mean is right in the middle of the data set. And we have a sample mean, so it's going to be X bar. And it is 64.2 inches because it tells us the mean, the sample mean was 64.2 inches. Now it's also giving us information about the standard deviation. So we're going to label off that 34% that's one above and 34% that's one below. So here we have 34% of data. Here we have 34% of data. And then the numbers that we'll label this is going to be X bar plus S, so one standard deviation. So we have 64.2 plus the standard deviation of 2.9. So this data, this point right here will be labeled 67.1 inches. And then below the mean, we do X bar minus one standard deviation. So 64.2 minus 2.9, which gives us a value of 61.3. So now I could tell you that 68% of women between the ages of 20 to 29 are between 61.3 and 67.1 inches. But they want to know between 58.4 and 64.2. So we're going to keep going. And we'll go out 2 standard deviations now. So now I have X bar plus 2 standard deviations over here and X bar minus 2 standard deviations on the left side. And remember that each of these is 13.5%. So I need to add another 2.9 onto my 67.1, which gives me a value of 70, and subtract another 2.9 from my 61.3, which will be 58.4. And just for fun, we'll go out to the third standard deviation away. So X bar plus 3S over here, X bar minus 3S over here. And each of these was just that tiny 2.35%. So add another 2.9, so 72.9 here, and subtract another 2.9, 55.5. Okay, so the question was, estimate the percent of women whose heights are between 58.4 and 64.2 inches. So here's my 58.4, here's my 64.2. So that's going to be all of this data within these two sections here. So the percent of women that are between 58.4 and 64.2 inches would be 13.5 plus 34, so 47.5%. Now I want to go back to that idea of unusual and very unusual, working with this same example here. Remember that to be considered very unusual, we have to be more than 3 standard deviations away from the mean. So let's figure out how tall we'd have to be considered a very unusual height. So to be considered a very unusual height, how tall would a woman, of course, age 20 to 29 in the United States, be? So how tall would a woman be if they were considered very unusual? Well, very unusual is more than 3 standard deviations from the mean. So we go out 3 standard deviations. So they would either need to be taller than 72.9 inches, or they could be on the other end. So we go out 3 standard deviations, and they would need to be shorter than 55.5 inches. Now, how many feet is that? 55.5 divided by 12. Whoops. That's like 4 feet, 7.5 inches. And 72.9 would be 6'1" almost. 6'1". So if you're taller than about 6'1" or shorter than whatever I said, because I forgot already, then you are considered a very unusual height for ages 20 to 29. Okay, the empirical rule, remember, only applies to data that has that very specific shape. But we don't always have that shape, so we have another rule that we can use. So just a reminder, the empirical rule only applies to bell-shaped distributions. Those are also called normal distributions. All other distributions, any other shape, follow something called Chebyshev's theorem. So we should probably talk about that. Chebyshev's theorem says that the portion or percent of any data set lying within k standard deviations of the mean oh wow, I spelled that weird, is found by doing this at least 1 minus 1 over k squared. So if we want to know what percent of a data set that's not a normal distribution that lies within 7 standard deviations of the mean, we would do 1 minus 1 over 49, and that would give us the percent of the data set that's within 7 standard deviations of the mean. So let's look at a little, for example. If k equals 3, then 1 minus 1 over k squared would be 1 minus 1 over 3 squared, which is 1 minus 1/9, which is 0.8 repeating, because 1 minus 1/9 is 8/9. So that would be 0.8 repeating. So what does that mean? That means that at least 89% of the data values of the data lies within 3 standard deviations of the mean. Now that does hold true for the empirical rule, because under the empirical rule, it's 99.7%, which is at least 89%. But if it's a normal shape distribution, then we want to use the empirical rule because it's more specific than Chebyshev's theorem. So we'll do an example using oddly shaped distributions that follow Chebyshev's theorem here. So what we want to do is figure out, well, there's no question asked here, but I'm going to write a question down here. What I want to know is what percent of ages fall within 2 standard deviations of the mean. So let's work with the data for New York. Okay, so they've given us this distribution, and it tells us in here to apply Chebyshev's theorem to the data for New York using k equals 2. I guess those are our instructions. That's what we're supposed to be doing. And what that means is to figure out what percent of ages fall within 2 standard deviations of the mean. And then we're also going to figure out what ages go with the 2 standard deviations so that we can make a sentence. So at the end of it, in order to apply Chebyshev's theorem to that data using k equals 2, the end result is going to be a statement that says at least some percent of New Yorkers are between something and something years old. So when we use Chebyshev's theorem to find the percent, that's going to go here. And when we figure out what ages go with those 2 standard deviations, that's going to go here. Okay, so what percent of the ages fall within 2 standard deviations of the mean? Well, that's just a straight application of Chebyshev's theorem. So that's going to be using that 1 minus 1 over k squared formula. So we'd have 1 minus 1 over 2 squared, which is 1 minus 1/4, or 3/4, which is 75%. So by Chebyshev's theorem, at least 75% of New Yorkers would be between 2 standard deviations of the mean. Now we got to figure out what those ages are. So what goes with the 2 standard deviations from the mean? Well, our mean is 38.8, so somewhere in between here, there's our mean. Notice that this is a population mean and a population standard deviation. So since our mean is 38.8 and our standard deviation is 22.5, then to go 2 standard deviations above and below, we would need to take the mean, and then we're going to do plus and minus 2 times the standard deviation. So our mean was 38.8, and that will be plus or minus 2 times 22.5. So 38.8 plus or minus 45. 38.3 minus 45 would be negative 6.2. 38.3 plus 45 would be 83.8. So since we can't really be negative 6.2 years old, we'll just call that 0. So at least 75% of New Yorkers are between 0 and 83.8 years old. We're going to shift gears a little bit and talk about finding standard deviation for grouped data. So what that means is that we are going to have individual data values, but they are going to be in a frequency distribution. So we'll have more than one of each of our data values. So rather than just listing out all of the data values, we're going to have a table that has data values and then frequency, and we'll use that to find sample mean and sample standard deviation. So there's going to be formulas here. So sample mean specifically for a frequency distribution. that formula is, since it's a sample, it will be x bar. X bar equals, it's going to be the sum of x times f. Remember, x means the individual data value, f means the frequency, and then we're going to divide by n, which is the sample size. And then we'll need a formula for sample standard deviation. For a frequency distribution. And that is going to be S equals the square root of, we're going to add up a column that we create that is the data value minus the mean squared. Then we're going to multiply that by the frequency. And that's what we're going to add up. So we take the data value minus the mean, square that, multiply it by the frequency, add up all those numbers, and then divide it by n minus 1, since we're using sample data. And then it's the square root of all of that stuff. So we have an example for that. It's the number of children per household in a region. I think I'm going to rip that off and scoot it up. Because I feel like I'm going to need more room there. Okay. You collect a random sample of the number of children per household in a region. The results are shown in the table at the left. Find the sample mean and the sample standard deviation of the data set. So our first task is going to be to create a frequency distribution so we can use our formulas. So we're going to start with data values, which will be the number of kids per household. So that is going to be x, our data values. And our smallest data value is 0. And then we have 1, 2, 3, 4, 5, and 6. 6 is our largest data value. And then we need the frequency for each. So now I'll have a column for F, which is frequency. So I've got to go through and count how many of each number I have. So zeros, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 zeros, ones, $19 of those, twos, looks like 7, threes, seven of those as well. Only 2 4s, 1 5, and 4 6s. So when we add that column, remember the sum of the frequency column. So that's 29, 36, 43, 44, 45, 50, 46, 50. So 50 would be the sum of our frequency column, which is going to be our sample size, which is good because it tells us that there are 50 households. Now, in our formula, we have x times f. So I'm going to make a column for that. And then I'll just multiply 0 times 10, 0. 1 times 19, 2 times 7, 3 times 7, 4 times 2, 5 times 1, 6 times 4. And notice also in the formula, we have to add that column up. So that's how we're going to get our sample mean. So next I will add these up. The sum of x times f. So 19 plus 14 plus 21 plus 8 plus 5 plus 24. That is 91. So the mean x bar is going to be, that formula says, the sum of x times f divided by n. So there I had 91 divided by 50, which is 1.82. Let's see. I think that comes out to be exactly that. Yes, 1.82. Now I know the round off rule says to go one data value or one decimal point past the data value, but also I'm going to need to use this value in further computations, and I don't want to round until the very end. So I'm going to keep that 1.82, and then in my final statement, I will round it when I give my answer. In the formula for S, it's the square root of the sum of x minus x bar squared times f divided by n minus 1. So I'm going to make a column for x minus x bar squared, and then I'm going to make a column for x minus x bar squared times f. Maybe I'll make a column for x minus x bar and then x minus x bar squared. And then x minus x bar squared times f. Ultimately, this column over here is the one I need to use. All the rest of them are like in between steps. So x here is 0 minus x bar, which was 1.82. So I'm going to do 0 minus 1.82. So that's negative 1.82. And then I'll square that. That's 3.3124. And then times the frequency, which was 10. So times 10, 33.124. And I'm just going to go along in that same manner through the rest of it. So I'll take x, which is 1, minus x bar, which was 1.82. That's negative 0.82 times the frequency, which was 19. Oh, excuse me. I need to square that first. Negative 0.82 squared. Let's just do that again. 1 minus 1.82 squared. There we go. 0.6724. Now times the frequency of 19 gives me 12.7756. And then we keep on going. 2 minus 1.82, 0.18, square that, 0.0324 times the frequency of 7, 0.2268. 3 minus 1.82, 1.18, square that, 1.3924 times the frequency of 7, 9.7468. And again, the data value minus the mean. 4 minus 1.82, square that, times the frequency, which was 2, data value minus the mean, square that, multiply by the frequency, which was 1, so 10.1124. In our last row, data value minus the mean, 4.18, square that, multiply it by the frequency, now in my formula, I'm adding up this column right here. That's what goes in my formula. So this value that I get here is going to go right here in my formula, because this, adding up all the row, is this part. Or excuse me, adding up that whole column. So you need your calculator, add up all those values. If you don't want to type them in again, I mean, you may be able to arrow back through. I don't know which is more time consuming, if you arrow back through and add them all up that way, or if you just type them all back in. I guess that's going to be a judgment call on your part. So when you add them all up, you're going to get 145.38, I believe. Hopefully that's correct. So we'll put that value, 145.38, into our formula, and then divide by n minus 1. N was our sample size, that's 50, so we're dividing by 49. So we'll take 145.38 divided by 49, and then we want the square root of that. So that is approximately 1.722480414. So at this point then, we would want to state our answer using that round-off rule, because they wanted the sample mean and sample standard deviation. So our sample mean would be 1.8 children per household. And our sample standard deviation would be, we're going to round to one decimal place further than our data, which were whole numbers. So that will be 1.7 children per household. So now if we knew whether that followed the normal distribution, then we'd be able to tell what would be an unusual and a very unusual, what percent would be in there. But as it is, I can still tell you that 1.8 plus 2 times 1.7, 2 standard deviations from the mean. If you have 5.2, more than 5.2 children, so 6 children or more, would be considered unusual. And 1.8 plus 3 times 1.7, 1.7, not 0.17. If you have more than 7 children, it would be considered very unusual, and vice versa. I can subtract 2. So if you have fewer than negative 1.6, it would be considered unusual, and I would agree with that because that's kind of an unusual amount of kids. Now let's look at what we do when we have classes of data in a frequency distribution. So instead of having individual data values, we don't know what all the data values are. We just have a frequency distribution that has classes. So since we don't have individual data values, we won't be able to know the exact value for the sample mean and standard deviation. So all we can do is estimate. We can estimate the sample mean and sample standard deviation. And we're going to do that using class midpoints, since we don't have the individual data values. So remember that class midpoints, I don't know if you remember, that was x sub m, and we do that by taking the lower limit plus the upper limit and dividing it by 2. So the formulas that we'll use for that, since they're samples, they'll be the Roman letters. So x bar equals the sum of x sub m times f divided by n. And the sample standard deviation will be s equals, it's going to be a square root thing again, square root of the sum of. What we'll do is x sub m minus x bar squared times the frequency, and then divided by n minus 1. So it's basically the same formula, except we don't have data values. So instead of using the data value times frequency, we use the midpoint times frequency. And instead of using the data value minus the mean, we use the midpoint minus the mean. So we won't know the exact value for the sample mean and sample standard deviation, but this will give us a good estimate. So we're going to use this spending before traveling example here. So the figure at the right shows the results of a survey in which 1,000 adults were asked how much they spend in preparation for personal travel each year. We're going to make a frequency distribution for that data and then use the table to estimate sample mean and sample standard deviation of the data set. So what travelers spend in preparation for personal travel each year. So here's our classes. Our classes are, so less than 100, I would make that 0 to 99, and then 100 to 199, 200 to 299, 300 to 399, 400 to 499, and then 500 or more. And we'll talk about how to handle that in a second, because remember, that's something that we call an open class. So putting together our data, we're going to have a column for classes. So remember, our classes were 0 to 99, 100 to 199, 200 to 299, 300 to 399, 400 to 499, and 500 up. Then we will put the frequency and the midpoint. So we might do the midpoint first and then the frequency. So the frequency is going to be given by the table. So less than 100 would be 380, 100 to 199, 230, and 210. That's looks like a 50. I couldn't tell if it was a 5 or a 3. 60 and 70. So our frequency should add up to our sample size of 1,000. So I'll just double check that. Yes, 1,000. So then to find the midpoint, we're going to take the lower limit plus the upper limit, divide by 2. So 0 plus 99 divided by 2, 49.5. 100 plus 199 divided by 2, whoops, 59. That's not right. 100 plus 199 divided by 2, 149.5. 200 plus 299 divided by 2. Now, are you seeing a pattern here? We have a class width that is 100. So the midpoints will all be 100 away from each other. So this one will be 349.5 and 449.5. And then let's talk about that open class. When you have an open class, you are just going to have to assign a value for the midpoint. So kind of a good rule of thumb there, or what I'm going to follow at least, is that I'm just going to follow that same pattern. So I'll just go with 549.5. But know that that just, oh, actually, they wanted us to do 599.5 for some reason. Hopefully we won't come across any of those in the exercises that we do. If you do, I'm hoping that they'll tell you what to assign for that midpoint. If not, you and I will just have to figure it out together. But we're going to use 599.5 here. So then we have our midpoints and our frequencies. In our formula, to find the mean, we need to do the midpoint times the frequency and then add that column up. So I'm going to make a column for x sub m times f, and then I'm going to add that up. So I'm going to do 49.5 times 380. That's a big number. And I'll just keep going. And then I want to add all of those numbers up. So again, if you want to, you can use your calculator to help you. If your calculator has this feature. If not, you'll have to just type them all in. So I get 192,000. So that's going to help me figure out my mean because it's adding those up, dividing by n, which was our sample size. So x bar will be 192,000 divided by the sample size of 1,000. So our mean is 192. Then we're going to do the next formula here, x sub m minus x bar squared times the frequency. So we need an x sub m minus x bar, x sub m minus x bar squared, and then x sub m, that was big, x sub m minus x bar squared times frequency. Now it's this last column that we're really after. I may just not write this column down because we don't really use it for anything. Well, we didn't really use this for anything either, but I'm not really comfortable just only going to this column. So we'll skip writing this column on this problem, and we'll write this one, and we'll write that one. So I'm going to have to take the midpoint minus the mean of 192. So I take 49.5, that was my first midpoint, minus the mean of 192, and then I'm going to square that number. That's 20306.25, and then times the frequency, which was 380. That's 7716375. And we just go along in that same manner through the whole thing. So 149.5 minus 192, square it. Times the frequency, which is 230. And we keep going. So the midpoint, 249.5, minus the mean, 192. Square that. Times the frequency, midpoint minus mean squared times frequency midpoint minus mean, square it, times the frequency, and last one, midpoint minus the mean, square that. Times the frequency. Okay. Now when we get done with all of those computations, we need to add that column up. So it's the sum of x sub m minus x bar squared times frequency. And that's what's going to go in our formula. So S is going to be the square root of whatever we get here divided by n minus 1. N was 1,000, so divided by 999. So add up all those numbers. Okay, when I added all those up, I got 25,668,750. So that's what goes in my standard deviation formula. So I will take 25,668,750 divided by 999, and then the square root of that answer, 160.2948672. And when I give my answer, I will round using the round off rule. So my sample mean would be that 192, and I don't need to round it. So $192 per year that would be spent on in preparation for traveling. And then my sample standard deviation So I've got to go one decimal place further than the data. So it'll be 160.3. And since it's money, I'll put $160.30. And that is per year. And that would be spent on preparing for personal travel. Okay, somehow I paused the video and didn't restart it, so I don't really know where that happened, so I'm just going to start at the top of this page. When we want to compare data sets, like to say which is more spread out, so like, for example, if I wanted to compare the test scores for first hour versus second hour, those test scores are using the same units, and so I can use standard deviation to figure that out. But if I wanted to compare something like height and income, those are not using the same units, so I couldn't use standard deviation to figure out which data set is more spread out. Similarly, if there are different means, so if I wanted to compare the heights of 2-year-olds versus heights of adult men, even though they're the same units, the means are going to be so different that we couldn't use standard deviation to compare them. So how can we compare the spread or variation of data sets with different units or different means? We mentioned it at one point. I told you that it was the coefficient of variation, but I didn't really go into any other detail. So to find coefficient of variation, we're going to take the standard deviation and divide it by the mean, multiply by 100. That's going to give us a percent. And then the higher the percent, the more variable or spread out the data is. So when you're working with a sample, the coefficient of variation, CV, is S over X bar times 100. If you have a population, then the coefficient of variation, CV, would be sigma over mu times 100. So the example that we're going to do is comparing heights and weights of a basketball team. Heights are obviously measured in inches. Weights are measured in pounds. Since we've already used the tables to do means and standard deviations, I'm going to let us use our graphing calculator to find that. So go ahead and put all of this data for heights in L1 and the data for weights in L2, and then we will use the graphing calculator to find the mean and standard deviation and go from there. Okay, so I have my data in L1 and L2. And in order to figure out the mean and standard deviation, we will go to stat and then calculate. And we want one variable statistics using L1. We don't have a frequency list, so then we go to calculate. And it's telling us that the mean is 72.75. And then remember, we'll have two values for our standard deviation. One is for sample, one is for population. Since this is population, we're going to be using sigma. So our coefficient of variation for heights will be the standard deviation of 3.3 divided by the mean of 72.8, since we're going one decimal place further than our data. So we'll take 3.3 divided by 72.8 and then times 100. That is 4.5%. Then we'll repeat that for weights. So stat calculate, one variable statistics. Change your list to L2 by doing second the number 2. Calculate that. So our population standard deviation is 17.7. Our mean is 187.8. 17.7 divided by 187.8 times 100 is 9.4%. So which data set is more variable? Since the weights are 9.4, then we would say weight is more variable than height. And that's because the coefficient of variation is higher for weights. So in other words, the heights are more clustered together. So we have the basketball players' heights are more similar to each other than their weights are. Or another way to say that would be that their weights are more different from each other than their heights are, meaning that they're more spread out or more variable.